We'll be looking at question 19 from the June 2019 paper. In this question, it's talking about industrial processes. Sulfuric acid is an important chemical used to make detergents, fertilizers, and dyes. It is manufactured in a multi-step process. In the first step of the manufacture of sulfuric acid, sulfur dioxide can be made from the combustion of hydrogen sulfide, and the equation is given there. Explain why the enthalpy change is a negative value. So we know this as exothermic. You see, whether a reaction is exothermic or endothermic, it really depends on the magnitude or the size of the bonds made and the bonds broken. So what it is, the idea is that more energy is released when bonds are made or formed than energy required to break the bonds. Yep. Next question is asking us, zoom out a little bit. It's asking us about the feasibility of a reaction. Feasibility, you see, they've given us individual entropy values. So let's work out the entropy change. We know that the entropy change is equal to the entropy of the products minus the entropy of the reactants. So the equation, so 2 times SO2, which is 248, plus 2 times 70, minus, open bracket. Now the reactants are 2 times hydrogen sulfide, 206, plus 3 times 205. If it makes you feel, you see, when you type these into your calculator automatically puts brackets around whatever is multiplied together. So that's that. Let's see what that gives us. Minus 391. It's in joules per Kelvin per mole. We will need to convert that into kilojoules. It's a negative value, meaning it's losing entropy. Why is it losing entropy? Because we've got 5 moles of gas. 3 plus 2 is forming 4 moles of gas. 2 plus 2. That's why it's a negative entropy. Now, is this reaction feasible? We're going to use that expression, delta G is equal to delta H minus T delta S. Delta G is equal to the enthalpy change of minus 1125. The question, minus the temperature is 20 degrees, but let's convert that to Kelvin. That plus that multiplied by delta S, which will be 3 minus 391 over 1000. Just put double brackets around this all. And that will give us our answer. I've got here minus 1010437. So, minimum 3 sig figs. Yeah, 3 sig figs minimum up to calculator value. We'll leave it at that. Now, the thing is, because delta G is less than 0, because it's a negative value, therefore it makes it feasible. Feasible. Yeah, that covers all the 4 marks. Moving on. This is a bit of a interesting question. You see, calculate the enthalpy change of formation of hydrogen sulfide using the enthalpy change for reaction 1. You see, they want you to work out the enthalpy change of formation of hydrogen sulfide. Now, formation is where 1 mole of a substance is formed from its elements in their standard state. Okay, so put like that, and you've got formation of these two because you've got sulfur reacting with oxygen and hydrogen reacting with oxygen to give you water as well. How many waters will be there? How many oxygens? 2. What's tricky about this is they have actually given you enthalpy change of combustion values. Now, you see, enthalpy change of combustion of S is actually the enthalpy change of formation of SO2. And it's also the enthalpy change of formation of H2O, because these are elements in their standard state. They're reacting with oxygen, which is also in its standard state. So these give you formation values. The fact that they've given you it as combustion, it's easy to get confused. I hope that makes sense. I'll just repeat that. The enthalpy change of combustion of these two is the same as the enthalpy change of formation of these two. So they're playing on words here. Now, the enthalpy change of reaction is given here. They want us to work out the enthalpy change of formation of hydrogen sulfide. So really, that's 2x, because you've got 2 moles. We only want x on its own, plus 3 times 0. Why have I included that? Because the energy change, oops, I pushed, this should have been a 3 here. The energy change from 302 to 302, there's no change in energy there. So that's 0. We can even disregard that. And then we've got 2 times minus 296.8 plus 2 times minus 285.8. We plug that into our expression. Minus 1125 is equal to minus 2x plus, you're going against the first arrow, and then you're going with the second arrow. Times that there is minus 1165.2, and rearranging whatever you do to one side, you do to the other. So let's put 2x on the other side. That gives us minus 1165.2 plus minus 1125. Sorry, plus. So that shouldn't be there. And then we divide that by 2. Enthalpy change of formation is where 1 mole of a substance is formed from its elements. That's why we're dividing by 2. Minus 1165.2 plus 1125, and then divide all of that by 2. The answer is minus 40, wait a minute, plus 1125. Yep, and then divide that by 2. That gives you 10 minus 10.05. They've not asked for specific. I'm just looking, does it say up to calculator value? Yeah, they're not, yeah, the question hasn't said. Sorry, wait 1 minute. Bear with me, ladies and gentlemen. Let me redo the calculation. Minus 1165. Yes, it's all right. You can ask away. Which one is that for? Oh, sample bottles. I can't remember what it's for. Yeah. Oh, to put the solid in. That's all right. Apologies about that. So minus 1165.2 plus 1125 gives us that. And let's divide that by 2. Yeah, it gives you minus 20.1. That's fine. The mark scheme allows just minus 20 to get all 3 marks. Good. Moving on. Write an expression for Kp, include units. This is product over reactants. You see, this is Kp, so we use partial pressures, and we use the curved brackets, SO3, and we raise the powers of the big numbers. 2, and then you've got your partial pressure of SO2 times the partial pressure of O2. That's your expression. And the units, so they give the pressure in ATM, atmospheric pressure. So what you've got ATM squared over ATM, should be a 2 there, squared times ATM. These cancel out, and it's 1 over ATM. So that will be ATM to the -1. Yep. Species. Yeah, allows without. They were showing gas. Partial pressure is of gases only. They wanted to see gases, but they will not penalize you for not including them. Determine the value of Kp for the equilibrium at 1000 Kelvin. Show what you're working out. You see, we're going to use an ice table. Why are we going to use an ice table? Is because there's a before and after thing happening here. Ice is initial. C is change. E is at equilibrium. Ice. It tells you in the question that initially how much SO2 are we using? The container, and then adds 12 grams of O2. Let's see how much moles is 12 grams. 12 divided by 32. So that's 0.375 moles. They've added some SO2, we don't know how much. Do we know how much SO2 they've added? No, we don't. There's 0 amounts of the product. Wait a minute, that should be an SO3 there. So we don't know the change at equilibrium. There is 0.350 of SO3. 0.350. You see the change, you've gained 0.350. The ratio they're being a bit cheeky here. They've given you the volume of the gas. They've given you the volume of the gas. So it's going to be 10.2 divided by 24 at RTP. 10.2 divided by 24. So this is 0.425. Now, you've gained that much. It's a 2-to-2 ratio. Then you're going to lose that same amount because these are in a 1-to-1 ratio. O2 is going to be half of that amount lost, minus 0.175. That leaves you with 0.200 at equilibrium. And that one will be 0.075 left. So you got your equilibrium moles. What we then do is work out the mole fractions. Mole fraction is the mole divided by the total moles. So that's going to be 0.075 divided by the moles added together. This one will be so these mole fractions, let's work them out. I'm just working this out. These two add up to 0.44. So I can predict that this will be 0.56. But let's just work that as well. 0.35 by 0.625. Yep, 0.56. Because the mole fractions add up to 1. And what we now do is multiply all these mole fractions by the total pressure, which is given as, sorry, the total pressure, yeah, which is 2.5 atm. Let's times all of them by 2.5. And these give you the partial pressures. Zero 0.3, 0.8, 250. I didn't, should be 250. 0.56 times 2.5. That's more like it. 1.4. 1.4. These partial pressures should add up to the total pressure. So 0.3, 0.8, it's 1.1. Yep, these add up to 2.5 atm. And so we work out Kp, products over reactants, 1.4 squared over 0.3 squared times 0.8. Three significant figures. We've got here 27.2. 27.2 gets you all the 5 marks. Wonderful. If you don't know where the 5 marks are from, 425. So you get 1 mark for this, 1 mark for this. Sorry, 1 mark for both of those. You get 1 mark for these. 625. Yep, you get 1 mark for the total mole. You got the partial pressures, which are over here, and the last mark for the answer. Wonderful. This question here, it's saying the chemist repeats the experiment at different temperatures. So I'll draw the equilibrium setup again. So we can refer to this. Is anyone there? Is anyone still listening after all these videos? If you are there, maybe give a like to the video. It just shows me someone's there. Sometimes I do think I'm talking to myself. You got the equilibrium set up there. It says the chemist repeats the experiment at a different temperature. The chemist finds that the value of Kp is greater than the original answer. Remember, Kp expression is products over reactants. Now, if if the Kp value has gone up, that means the partial pressure of SO3 must have gone up and the partial pressures of the reactants must have gone down. That means that the equilibrium has shifted to the right. If it's shifted to the right, and we know that the forward reaction is exothermic, so the forward reaction is exothermic, the reverse is endo. That means the temperature must have been lower than 1,000 degrees, 1,000 Kelvin. So we say lower temperature as forward reaction exothermic. 1 mark. And the second mark is because the equilibrium, based on this bit here, equilibrium has shifted to the right. Explain the significance of this expression Kp. It's a double greater than sign. 1. If it's greater than 1, that means the equilibrium is far to the right. The equilibrium is far, far to the right. The equilibrium position is far to the right. That's what that means. If it's greater than, if it's less than 1, that means it's towards the left. We've got here another Boltzmann distribution question. In this question, we've seen a few of these Boltzmann distribution questions. Choose pink. You see here, explain vanadium 5 oxide is used as a catalyst, as a keyword buzzword here, catalyst. Explain how the presence of the catalyst increases the rate. Include a labeled sketch of the Boltzmann distribution. You see, ladies and gentlemen, let's label the axis. Number of molecules. These are molecules. At the bottom, we have energy. And our Boltzmann distribution starts off at 0, 0. It's like a camel hump. And it comes all the way down, but does not touch the x-axis. And because this is the original activation energy, by using a catalyst, it lowers the activation energy. It's called that EC. And by doing that, you've now got a greater proportion of molecules that have energy greater than the activation energy compared to the initial pink, therefore increasing the rate of reaction. So where are the 4 marks from? 1 mark is one mark of the curve, 1 mark for the axis, axis labeling, and yep, the EC shown towards the left. You get a mark for that as the 3rd mark. And in a statement that using a catalyst there are a greater proportion of molecules that have energy above the activation energy with a catalyst. Whether vanadium oxide is a homogeneous catalyst or a heterogeneous catalyst. The prefixes of homo and hetero. Homo is same, hetero is different. Same what, different what? It's in relation to the reactants and the catalyst in terms of the phases. So we write down heterogeneous catalyst as the catalyst is in a different. The catalyst is a solid and the reactants are gases, is in a different phase or state to the reactants. So the catalyst is a solid and the reactants are gases. And that is the end of that, ladies and gentlemen. Say less. See you tomorrow.